Hi everybody. I'm responding to a comment that was left on the YouTube channel, basically asking about the positive feedback aspect of the M-Cyclin CDK complex. So just a reminder, if we have G1 right here, synthesis G2, and mitosis here, the mitosis CDK complex, or the M-Cyclin CDK complex, is going to regulate the entrance into mitosis. So basically, nuclear cell division cannot happen unless the M-Cyclin CDK complex is activated. The M-Cyclin CDK complex is also called MPF and sometimes the MB1 cyclin in humans. You might also see CDK1. But what an interesting thing happens here, that is that the M-Cyclin CDK complex, both parts of it are actually built for large amounts of the cell cycle. And there are some things that can stop it from being built. That's P53. For example, if you have DNA damage, you will have a drop in expression of the M-cyclin, but it doesn't get activated till right about here. Once it gets activated, though, it gets activated in this like major ramp up. It's this super accelerated exponential ramping. And so let's look at exactly why that is. So a positive feedback loop is basically when you have the subject and a predicate as being the same thing as a sentence. For example, in this case, the M-Cyclin CDK complex activates the M-Cyclin CDK complex, which means that the M-Cyclin CDK complex also activates the M-Cyclin CDK complex. And I can just say that sentence over and over and again, and what I'm going to end up with is a bunch of M-Cyclin CDK complexes that are activated. A metaphor, if I'm driving down the road and my girlfriend is sitting to the right of me and I start to veer right a little bit, she might yell, "Turn left." That's a negative feedback system, a situation in which she is giving me a correction that is in the opposite direction I went. I was going right, she went left. She told me to go left. But if she's really, really mad at me, she might give me a positive feedback, which would be I start to turn right, and then she tells me to turn further right. So the moment I start to turn right a little bit, that right-hand turn becomes really severe. And in the case of the M-Cyclin CDK, it's the same exact thing. Once I start to activate the M-Cyclin CDK, I get a ton of activation. So why that is, so the M-Cyclin CDK actually acts back on the thing that activates itself. I know that didn't make any sense. Let me try to explain it. So here we have WEE1, which is an inhibitory kinase. Basically, this WEE1, this enzyme, puts a phosphate group on this CDK, inhibiting the M-Cyclin CDK complex. And the reverse is true. Basically, there is another enzyme which will go ahead and phosphorylate the bottom of the CDK. And so the M-Cyclin CDK leads to the inhibition, or it shuts down the inhibitory kinase. It turns off the off switch, which means it basically turns the whole thing on. And it also positively feeds back to the activating phosphate mechanism. So what you end up with is once M-Cyclin CDK is activated just a little bit, it shuts down the inhibitory aspects of its own production, and it activates the activating aspects of its own production. Again, we just jerk the wheel really, really far to the right, and that's a lot what the graph would look like too. It would be an exponential rise in M-Cyclin CDK as opposed to a linear one, which would happen if I just jerked the wheel to the right and then let it stay there. I hope that makes sense, and I hope that explains the exponential rise and the positive feedback system in the activation of the M-Cyclin CDK. Quick note, P53 and other tumor suppressors often activate to shut down M-Cyclin CDK production. And you often see the M-Cyclin CDK dysregulated in cancers because, like I said, it's the gatekeeper to mitosis. You basically can't have mitosis without the M-Cyclin CDK. If a cell can somehow bypass that stop and checkpoint, then it can proceed into mitosis without proper DNA division or with DNA damage. That's it. Hope that helped.